Welcome. I'm going to do a screencast here on how to represent energy, some different ways than you've seen in the previous screencast, which was very quantitative, very numerical. This is going to be more of a graphical representation, and I think it's going to help you understand how energy can be transformed from one form into another and how it can be conserved. And as we've talked about in previous screencasts, energy can't be created or destroyed in the universe. So whatever energy existed after the Big Bang still exists in the universe. It can be transformed into other forms. So it can be turned into chemical or thermal energy, heat. Chemical energy can be turned into kinetic energy like gasoline in your car, things like that. But the forms of energy that we're talking about in this unit, which is mechanical energy, that includes gravitational potential, elastic potential, and kinetic. Those forms can be lost, if you think about it, by being transformed into other less useful forms of energy. So even though mechanical energy we say is lost, that just means it's being transformed into thermal or internal energy like friction. And I'll give you some examples of that here in the next couple slides. So different ways to represent energy that we're going to talk about in this screencast are using a pie chart, using bar graphs. They each have their own advantages, and I think you'll see as I get through the examples what the advantages of each of those are. I think you're familiar with both of those kinds of representations. And we're going to also talk about how we're going to define a system in a worksheet today that I'm going to have you do for homework. And we're going to talk about in a closed system, energy can be conserved unless work is done by some outside force on the system. So when work is done by the outside force, energy is added to the system. So energy is not the same at the beginning and the end of some process if work is being done on the outside. And likewise, if the system exerts a force on its environment, so something that's not part of the system, if the system maybe is exerting a force on, let's say, a spring that's not part of my system, and the mass of a block is compressing that spring that is in my system, then the mass is doing work on the spring and it's storing energy in the spring. So the system would lose some energy in that case. So we'll go through all these examples, and I think it'll make more sense to you as I go through them. So this is a website that I would use in class if we were in class. It's called PHET. It's if you just Google PHET, you'd get to the website. I put the link down here at the bottom if you're interested in checking this out, because it's a lot of things you can do with this simulation. But what I'm going to do, it's basically like a skate park kind of thing. And we're going to have our skater start at the top, and we've got a little bit of friction. I'm going to add some friction here. Okay, so at this point, I'm going to hit the play button, and the guy on the skateboard is going to travel down the track. And let's just kind of watch his motion. Notice that the friction is present here. So he kind of just is not quite getting all the way to the end there, and eventually he's going to come to a stop. So if I restart, and I'm going to take friction down to none, watch what happens. So he sails off, okay? So clearly friction is taking away some of the kinetic energy of this guy as he's traveling down this skate hill. So I'm going to check out the pie chart here, and the pie chart's got three kinds of energy. I'm going to add a little bit of friction back like we had before, and you'll notice kinetic energy is green in the pie chart, potential energy is blue, and thermal energy is orange. So here we go. Oops. Restart skater. Got to add a little more friction, because I don't want him to leave. So you can see as he continues to go back and forth, that orange bar gets bigger and bigger until he stops. So all the green is gone when he stops. All that's left is orange and blue. He's still got some potential energy because he's still above the ground down here. So this level right here is above the ground. So he's got some gravitational potential energy, but he doesn't have any kinetic energy because he stopped moving. Okay, so let's go back to restart. And I'm going to get rid of the friction this time. Okay, here we go. I'm going to go slow motion. So as he's going, as he's coming down the ramp, see how the blue turns into the green kinetic energy. He gets to the bottom, and all of that potential energy has gone over to kinetic, virtually all of it. Okay, now he's coming back up again. Some of the potential energy goes back to kinetic, back down again. The potential, the blue, turns back into green. So it's all in the form of kinetic energy right there. And then a little bit of each. The higher he goes, the bigger the blue gets, and the less kinetic energy he has, the green. So that's a useful pie chart. The useful thing about the pie chart is it shows you that the amount of energy isn't changing. It's just whatever can fit into that pie, but it's changing forms between kinetic and potential. Now you notice there's no thermal energy there because I got rid of the friction. Over here I took the slider bar for the friction down to none, so you don't have any thermal energy. What's the bar graph look like? Really similar as far as that, only it's represented with bars instead of the pie chart. So I'm going to go ahead and restart the skater, and notice at the beginning you've got only potential energy. As he comes down the ramp, you see the kinetic energy getting bigger and the potential energy getting smaller, the bar over there on the left. And when he goes up a hill, the blue potential energy bar gets bigger and the green kinetic energy bar gets smaller, and so on. So two useful ways to represent energy. Again, if you want to use this PHET website, it's free. You can check it out, and there's a link right there. So the worksheet I'm going to have complete tonight, it's a graphical representation of energy, and you have to define a system in each one of these problems. So that's how we're going to start. These are the instructions. This is problem number 1A on the worksheet for homework tonight. It says list the objects in the system. So we're going to list the objects in this space right here in the circle, and always include the Earth's gravitational field in your system. Well, it turns out that with gravitational potential energy, to have gravitational potential energy, you have to have two masses. So we haven't talked about this before, but to have gravitational PEG, you must have two masses. Because if you think about a rock out in space, for instance, that rock that's out in the middle of space, that doesn't possess any gravitational potential energy. It only possesses gravitational potential energy if it's in the presence of the Earth's gravitational field. So you have to have the Earth present for another object to have gravitational potential energy. In fact, anytime you have two masses that are close enough to each other to interact and have a gravitational force between them, you're going to have gravitational potential energy. So it turns out that that energy is stored in the gravitational field. It's not truly stored in the object itself. It's stored in the field between the two objects. So anytime I've got gravitational potential energy in a system, I'm going to include the Earth in the system. So that's what it tells us right here. We're going to indicate our choice for zero height to measure that gravitational potential energy. I'm always going to pick the lowest point in the problem. And I'm going to sketch the energy bar chart before at position A over here, and then after at position B at some later moment. Notice these are instants in time. This is not a movie. These are two different snapshots of points in time. And then if work is coming into or out of the system, I'm going to show that with a giant arrow going in or out of the system. Okay, so I'll show it that way as we need to. Okay, so our system, in the first problem, it says, in the situation shown below, a spring launches a roller coaster car from rest on a frictionless track, so I have no thermal energy or internal energy, into a vertical loop. assume that the system consists of the cart, the earth, the track, and the spring. So cart, earth, track, and spring are in the system, okay? So what kind of energy? Here's a bar chart with energy on the y-axis at position A, and I'm going to represent, notice how they use different symbols for energy. It's not Ke, Peg, and Pee like in your textbook, but you get the sense this is kinetic, this is gravitational potential, this is elastic potential. So I'm going to define my 0 point to be Peg equals 0 at this point right here, which means at the beginning there is no gravitational potential energy, so I don't need to put a bar there. There's no kinetic energy, but there is some stored elastic energy. So I'm going to go ahead and draw a bar here, and it doesn't matter how tall I draw it. Mine's going to be made up of 4 blocks, 1, 2, 3, 4 blocks of elastic energy. Now we get up here at point B. You can see I'm above the 0 point for gravitational potential energy, so I've got some PEG, but I've also got some kinetic energy because you can see this thing is moving, you know, relatively fast at the top of the bar. So I have to take that initial energy from the system, the elastic energy, and I have to spread it between kinetic and gravitational. I'm going to give it 1 bar of kinetic, which means there must be 3 bars of gravitational. The number 4 here, these 4 bars here, 1, 2, 3, 4. I have to have 4 bars over here, 1, 2, 3, and 4. Okay, so I want to make sure it balances out. The qualitative energy conservation equation, all that is writing out qualitatively that PE, I'm going to use our textbook's notation, elastic equals initial at point A actually, equals the Ke at point B plus the PEG at point B. Notice there's no elastic energy at point B because the spring has completely released all its energy, and there's no thermal energy either because there's no friction with the track. So that's how you would handle those kind of problems. Let's do another one. And this is repeating problem 1A, but it's a frictionless system that doesn't include the spring. So it's the exact same problem I just did, the same physical situation. I'm just defining my system a little bit differently. So I've got the cart, and because I have gravitational potential energy, I've got to include the earth in my system, and I'll include the track itself, but not the spring. So if I don't include the spring, that means the system doesn't contain that energy at the beginning of the problem. So what happens at point A, or over the course of the process, there is work that's being done from the outside. So that's this giant arrow right here, and I'm going to draw a big arrow, and it's going to have the bars in the arrow. So there's my 1, 2, 3, 4 blocks of energy, and I'm going to call that work. The spring is doing work on the system, so it's putting work into the system, and at the end I have the exact same situation I had in the last problem. I had one bar of kinetic energy, and I had, 3 bars of gravitational potential. Exactly the same physical situation. It's just defining the system differently. So the spring in this problem was not in the system. So it was an external force that exerted a force over a distance. It's doing work on the system and adding energy to the system. So the system had 0 energy at the beginning. It has a bunch of energy at the end. Where did it get that energy? From the work done by the spring here during the process. So the way I write that down here, I say work equals kinetic energy at point B plus gravitational potential at point B. Okay, so what's different from the last problem is work done by the spring instead of elastic energy. Last one we'll do, this is problem 1C, and this one is the same as 1A, but now there's going to be friction. Okay, so it's the same as 1A, so that means the spring is part of the system. So I'm going to start out with my 4 bars of, I got to list my system here. So I've got the cart, the earth, the track, and the spring is back in the system again for this one. So I say I've got 4 blocks of energy at the beginning, but now because there is friction, there's going to be some thermal energy. I'm going to say I'm in trouble because I didn't give enough kinetic energy before, so I'm going to have to make this inconsistent with my last one. I'm going to have 1 block of thermal. I still have to have some kinetic, because if it's not moving at the top, I can tell it's moving. If it wasn't moving, it would fall. So I know there's got to be some kinetic at the top. But because these blocks on the left, these 4, have to add up to the number of blocks I have over here, I can only give 2 blocks to the gravitational energy. I should say 2 and 3 here. So there's the 4 blocks over there. So notice I have some thermal energy now because I have friction. So the way this would look is PE elastic at point A. At position A, I've got some stored elastic potential energy that's converted into kinetic energy at B, plus some gravitational potential energy at B also, and then some, let's call it thermal at point B. Okay? All right, I hope that helps you understand how to do worksheet 3. I did the first problem, A, B, and C for you. Go ahead and finish that for homework tonight. If you have any questions, you can email me or jump into one of our one of our office hour hangout meetings, Google Hangouts. Okay, take care, stay home, stay safe.